Okay, good. I think we're all ready. So let's get started. The topic for today's lecture is node centrality and ranking on networks. All right. So I'm going to go into some details of what that is and why it's important. So first of all, just a quick sort of summary of what we're going to learn is we're going to learn so that the meaning of the word centrality and prestige for the networks, and we're going to study different centrality measures that are used on the networks. And there's going to be degree centrality, closeness betweenness, and eigenvector centrality. And then we'll talk a little bit about ranking on directed graphs. So when your network has directions. So first of all, the main idea here is the following. When you look at the network, you realize that certain nodes or certain actors within the network are more important than others, right? And looking at this picture, this slide, you might sort of realize that, okay, maybe these guys are are quite important. They're in the center, and among them there are some nodes that are very connected versus other nodes are not that much within the center of the graph. You can also think of the situation where let's say you're thinking about propagation of information or like rumors from one group of nodes to another group of nodes, and then other type of nodes could be important, because if you think about it, nodes that are right here, they act as a bridge nodes, and they are important in terms of being a bridges in between, say, these nodes and these nodes. And so if information flows from there to, like, say, central nodes, these guys can be important in the sense of being the conduit of information, right? So there are different metrics of importance depending on where nodes are in the graph. So they play different roles. Now, if you can actually draw a picture like I just did, then again, you might be able to just like eyeball look at the nodes and say, okay, well, yeah, these guys, the sort of these guys are actually central. They're like sort of geometric center of the network, right? And these nodes live on the periphery of the network, and those that I showed in red are important when information being transmitted. It's all great except for when the network is very large, you cannot actually draw it, right? And it's very hard to just analyze the way I just described. At the same time, we could actually calculate certain metrics for nodes depending on where they are in the network, without actually drawing the network. And those metrics will carry certain meanings, like, for example, nodes being the most like geometrically centered, or the nodes being like the most important when information is being transmitted. And so we can calculate those metrics and use it to rank the nodes by their importance to the network. And that's what we're going to learn today. Make sense? Okay. And I think I also muted the classroom. Let me change that. Sorry, guys, just a sec. I'm trying to. That's terrible. I cannot unmute it anymore. Okay. So anyway, so that's the plan for today. That's what we're going to do. So let's look at this from a little bit different perspective. Now, this story comes from sociologists, and this is quite an interesting story. Now, if you look at this network, and this is a network of of Florentine's family marriages. Right, so these are different families back in Florentine in 15th century, and the edges there are the way those families are married into each other, right? So by looking at this picture, is there any one single sort of name, family name, last name that you actually know out of those? Ah, okay, yeah. Huh. It's all muted. So yeah, you can communicate through chat. So yes, so it's Medici, right? So Medici is, the interesting thing is Medici family. It was not the largest, and it was not the richest, right? But we still remember them out of pretty much all that collection. And so the question is, maybe it's a role, the Medici family got to prominence because of the way they formed these marriages. And that's actually that's one of the questions that in the paper by Paget in 1993 was where he was exploring it. And we'll see at the end of the lecture how Medici, how they rank compared to other families based on this network properties. Okay. All right. So one thing that we need to, like, whatever metrics we're going to build for the network, there is sort of certain common sense things that those metrics should satisfy. Like, for example, if we look at this at the first graph right here, right at this one, which node, I mean, whatever metric I come up with, which node should be the most central? You're actually on the mute. I don't know why I cannot hear you.
We hear you well.
Yeah, I know, but I cannot hear. Okay, I can hear you guys. So which node here should be more central? A, yes. Okay, good. Finally, I can hear you. Otherwise, it was like a radio. Okay, I'm like just speaking. So A, of course, whatever metric you come up with, A should be the most central, right? According to that metric. And the rest of the nodes, like this F, G, B, C, E, D, they should be, equivalent in terms of their centrality because they like, equally positioned, but of course they have to be less central than A. Now, if we look at this picture, what can we tell you about, like, whatever metric of centrality I can come up with? What can you tell me about centrality of those nodes? It should be equal, right? Because they have equal positions within the network. And again, if I look at this graph, which is a sort of line graph, well, it's sort of clear that this guy probably, again, whatever metric I use, should be more central than sort of these guys we're like on periphery. So these three graphs are those graphs that we kind of, metrics that we can come up with. We can, take those metrics, apply to this graph, and make sure they make sense, right? Just sort of satisfy common sense. Another important point here, notice that the graph is undirected here, okay? So that's the important story. Important part of this story. Okay, moving along. So the first and sort of the most obvious metric is called the degree centrality. Well, it is what you think it is. It's just sort of the number of direct connections of the node, sort of number of your friends, or the node degree. So it is what it's called, right? It's very, very simple. Now, one interesting thing you need to notice is that sometimes we can talk about the degree centrality, but sometimes it's worth talking about normalized degree centrality. Now, the reason with this we need this normalization is because if we want to compare nodes from the different graphs, in order to do that, you need not just to look at the maximum, the largest centrality of the node, but compare this centrality to the maximum possible centrality. What I mean is, if you have a network of 3 nodes, the largest centrality, say, this node can have is equal to 2, because it has, that's the maximum connectivity it can have. Now, if you can look at the network of more nodes, again, the largest centrality here is for the central node. It is equal to 1, 2, 3, 4, 5. So if you want to compare centralities within the network, within each network, of course, you can use just the degree. But if you want to compare them in between networks, this centrality, this degree is equal to 2, this degree is equal to 5. But, relatively within its own network, they're both the most central nodes. So in order to sort of take that into account, what you often do is you come up with this normalized version of the centrality, where you take the degree centrality and divide by the maximum possible centrality. So in both of these cases, the node we looked at has a maximum possible centrality, right? And the maximum possible centrality is number of nodes minus 1. Why minus 1? Well, because you take this node and you see what's the maximum number of direct connection it can have. Okay? Make sense? Yeah. Okay, good. So degree centrality is just the node degree or number of the direct connections. Okay? All right. Moving along. Now, the second type of centrality, is so-called closeness centrality. Now, closeness centrality takes care of the following fact. If we look, at the picture, if we look at this picture and think about just degree centrality, according to the degree centrality, the most central nodes are these 3, right? They have the highest degree. But at the same time, again, looking at this picture, you realize that, from geometric point of view, the blue node is the most central one, right? So we need somehow to come up with a way to pick up the nodes that are most central in a geometric perspective, like compared to other nodes. So, and this is done by the notion of closeness centrality. So the notion of the closeness centrality is defined the following way. It is inversely proportional to the sum of the distances from this node to all other nodes. So if I pick up, one node here, let's say this guy, and calculate the distances to all the guys in the network, right? That's going to be sort of these distances direct, then this distance, then this distances to pink nodes, and then again to this, then again to this, then again, etc., etc., etc. Add them up, I'll get certain number. Well, so the centrality will be 1 over that number, which means if that number is large, the centrality will be small. So if I take a different node, this guy, and add up distances from this guy to all the neighboring node, the sum will be smaller. And so inverse of that, 1 divided by the sum, will be larger. And so the closest centrality metric for this node will be larger than for the pink node. Do you see that? Okay. So in order to compute closeness centrality, you need to compute distances from from that node to every other node in the graph, and choose the one that is 1 over that number. Well, the good news again, it can be calculated easily, within within the iGraph package, right? So it's actually pretty easy to compute those numbers. Any questions here? Okay. So the third type of the centrality is interesting. It's called betweenness centrality. And the idea here is the following. Let's say, and let's look at the picture right now. So we have some node here and some node here. And think about, this is either city, and you need to get from, red type of nodes to blue type of nodes, just walking the streets. Or you can think about it as a social network, and the person, the edges are friendships, and you need to send a message. So you need to connect. You need to meet the person. Red person need to send a message to the blue person. In any cases, whatever example we consider, those sort of messages or walk should go through node A. We can pick up, another pair here, there. It's again will go through the node A. Now, if we pick up two nodes that are, say, here and also on the red side, then it doesn't have to go through A. But it's kind of clear by looking at this picture that A is strategically positioned such that majority of the, actually most of the shortest path from, red to blue will go through A, because that's the only bridge there, right? Again, think about like in St. Petersburg, right? Two sides of the city. Okay, you have to go through the bridge. So bridge has a strategic importance in here. And the way to compute this importance, to like sort of to put a number to it, would be, let's just calculate all the possible shortest paths that go between any two pair of nodes in the graph, and find the node through which most of those paths go. Okay? So if I just start calculating all the shortest path in between any pair of nodes, and for the nodes in between them, let's say I can pick up this node and try to compute how many shortest paths this node is on. And it's going to be, okay, this shortest path, this, etc. And I just count that number. Or I can do the same thing for this guy and see on how many shortest paths this guy is on. And of course, it's going to be this shortest path, but it's going to be that, it's going to be this, it's going to be this, it's going to be, this, and so on. And so if you calculate this, the numbers will confirm the obvious thing, which is obvious fact that this guy, the node A, sits on the largest number of shortest path. And so it's a bridge node. And that sort of the fact that it is a bridge node is reflected in betweenness centrality. And so that's what it is. So we're actually computing the number of shortest paths that go from any node to any node. So this actually says, let's sum over all the pairs of the nodes in the graph. We take into account shortest path that go through this particular node that is in question. And in this case, like on this picture, node I is actually node A. And we just divide by the total number of shortest path that goes between two nodes that go through some other node, but not through node A. And in this sense, in this case, everything goes through node A. And the same way as before, if you just want to understand the importance of the nodes in one particular network, you can just use this metric of betweenness centrality. If you want to compare the nodes that belong to two different networks, you have to normalize this by the maximum possible number of shortest paths in this network, in those networks. And that's what's done here. And again, n is total number of nodes, and that's how you compute like n minus 1 times n minus 2 divided by 2. That's sort of possible number of pairs that could exist. And that's why we're normalizing by it. Does this make sense? All right. So far, we talked about the degree centrality, and that tells you about direct connections of the node. we talked about, so what was that? What else was? We talked about closeness centrality that describes, geometric center, right, which is inversely proportional to the distances to all the nodes. And now there is a betweenness centrality that tells you on how many shortest path particular node stays on. All right, and so these three things actually emphasize very, very different properties of the nodes, and depending on the situation you're describing, one can be much more important than the other. Finally, there is yet one more metric that I want to touch upon, and that's called eigenvector centrality. So here the idea is the following. If you think about centrality as a metric of importance, right? So let's say we want to rank people by their importance. Then, maybe positioning in the center of the network, well, maybe it's good, maybe it's bad, right? Having a lot of direct connections, let's say direct friends or direct followers, might be important, might be not. Because what really, let's say you think about business. Well, the question is who your friends are, right? If you're friends with their, CEO of the company and top officers, you're probably, more important within the network, though you don't have that many friends among your colleagues. Now, think about social networks. If you're friends with celebrity, your status within that network actually can be much higher than if you have like 20 friends, but each friend is like sort of just regular Joe. Okay, so the idea here is that it is important who your friends are, and your importance is based not only on the number of friends you have, but based on their importance. So what do you think about that idea? Good, bad, interesting? Interesting. Okay, so you're not buying it yet. All right. So if you look at this picture, it's actually the size of the node here tells us about this eigenvector centrality importance. And if you notice, what happens is that the large nodes connected to the large nodes, right? And the small nodes connected to even smaller nodes. So within this kind of framework, you cannot be important if your friends are unimportant, right? It's sort of self-enforcing kind of property. To compute it, what you do is it's not as easy as sort of the previous three importance factors. The way to do it is the following. You're saying your importance or the node importance is actually depends on the importance of the direct neighbors of the node. And so what it literally says is the importance of the node is equal to the sum of the importances of its neighbors. So I would say, if I try to calculate this, I would say, okay, I want to compute the importance of this node. I need to take the importance of their direct neighbors, add them up, and that will give me the importance of this node. I mean, it sounds like a plan. The only problem is, in order to do that, you need to know the importance of these guys, right? But to know the importance of these guys, you need to know the importance of its neighbors. So you need to to compute importance for this, for Nancy, I need to know importance of her friends, and so on and so forth. So it feels like it's a recursive process, and it is. Well, the good news, if the graph is undirected, like the one shown here, very often this process converges. Now, in order for it to converge, you actually need to do a little modification. Instead of just adding things up, just adding the values on the neighbors, you have to also normalize them by some constant. And the reason for that is because otherwise the importance will keep increasing, because you're just adding up importance of your neighbors, and that's your importance. But now when you compute your neighbors, that takes into account your importance, so it gets even larger, 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 larger. And so in every iteration, you have to normalize it, and that's what you do by dividing by some coefficient lambda, and that actually converts this problem into eigenvalue problem, eigenvector problem, where A is adjacency matrix, and you actually can solve this eigenvalue problem and calculate the importance vector. That vector corresponds to the largest eigenvalue, and it's called eigenvector centrality. Okay, how many of you actually remember what eigenvalues and eigenvectors are? Or how many of you guys never heard about those? Okay, I don't see any hands in either answering either of those questions. So do you know what eigenvectors and eigenvalues are? Do you remember that? No?
How will be in Russian?
Собственные значения, собственные вектора.
I remember.
Okay, so that's better. Yes, so the traditional you would write them ax equal lambda x. All right. So that's eigenvalue problem where x is a vector, a is a matrix, right? You have a matrix times a vector if it's a number times that vector. Linear algebra, linear algebra, первый курс. All right, for those who do not remember, maybe Ilya Andreevich will spend a few minutes today and just reminds you what they are. Now, again, the good news for you is that, of course, there is within iGraph, there is a function you call, and it just calculates them for you. So you really, you really don't have to compute it, but it would be good if you understand sort of at least what type of object that is. But again, the main idea is that, using eigenvalues, eigenvectors, so what you do is you calculate the importance of the node as literally an sort of average or weighted sum of the importance of the neighbors. And the key message here, you cannot be important if your friends are unimportant. And the more important friends you have, the more important you are. All right? I'm not saying it's fair, but that's what it is. That's how it's being computed. So these are 4 sort of basic metrics we could use to, classify or to rank the nodes on the network. Because now you can take every node, any node in the network, calculate those metrics and tell me like, okay, if I want the most central person in the sense of like betweenness, so the most shortest path goes through him, maybe, if it's organization, this is a guy who knows everything about organization because all the news, all the gossips go through this guy. Here it is, it's between the centrality. Or if I want the most popular guy, or girl in the network, then it's a guy who has the girl who has the most direct number of direct connections, right? That's degree centrality. Or if I want to know group of people who are very influential in the network, that's eigenvector centrality, because influential people will be connected to influential people. So just for you to understand better, what the heck? I want to give you an example of a network, and with the computed centralities. Oh, and by the way, here is how you call it within iGraph. So this is a network, and red nodes here are those that have the largest closeness centrality. So these 5 nodes have the largest closeness centrality. Now, on the next slide, I will show you nodes that have largest betweenness centrality. But before seeing that graph, before seeing that result, can you guess which nodes on this graph will have, several largest betweenness centrality? Can you speak it up a little bit more? Sort of something like this, guys. Yeah. So something is those that are bridges, right? Those that are sitting in between. Well, let's see. Okay, here they are. So we almost guessed correctly, right? There's this guy, you know, here is another one, here is another one. So this is those bridges. Now I probably missed this one, would miss this one, but you know, it's also a bridge because there are quite a few nodes here and everything goes through that node, all the connectivity from those guys. Okay, one more guess. So we did, you know, closeness centrality, we did betweenness centrality. Then there is this eigenvector centrality, right? This strange thing where, you know, influential connected to influentials. Now, what would you expect as a sort of which nodes would you expect to have high value of that centrality? Yeah, eigenvector centrality. I mean, it's a tough question. It's not an easy guess, but yeah. So it's going to be those nodes that are kind of grouped together, right? So those are very well connected. They will all have, you know, high values. And you know, let's just take a look at this, right? So the strongly the most connected nodes are here, and that they get the highest eigenvector centrality. I mean, I don't show in this graph anywhere on the previous graphs the degree centrality, but it's sort of obvious. So, and by the way, this is how you compute this eigenvector centrality. So the goal of those like last 4 or 5 slides was to show you that how you can actually compute those centralities, right? And how they're different. So when you have a network, if you want to look again, find the nodes that are all connected among themselves and sort of enforce each other importance, you know, you go for eigenvector centrality. And if you're trying to look for the nodes, you know, that are on the most short, on the largest number of short spot, you go for betweenness. And you know, if you look for the most central geometric nodes, you go for closeness centrality. All right. Any questions on the centrality topic?
I have one question. So what will be the physical value from those different centralities for those nodes? For example, if this was a social network, so if we take eigenvector centrality, those people should be something like most, should have most money. I don't know. And so this different centrality should show us different
Properties, right? Different mapping on the, yeah. So for the social network, like again, the degree centrality. Thank you for the question. For, you know, the degree centrality will show how many direct friends you have, which is obvious. Now, betweenness centrality will show on how many short spots between different people you are, which means, you know, if we consider propagation of news in the network, or, you know, sort of friendship, how important you are to that network. If I remove this person with high betweenness centrality, the network will get disconnected easily. And eigenvector centrality, this will be the group of people who are you know, the most influential, in the sense that their friends are also influential. It's like, you know, in high school, you know, you've got cliques of group of people who are like group of students that are like form cliques of, like, you know, the important students in the class, right? So that's sort of the meaning in the social networks. But we can also look at, again, at any other network. If you think about this as a road networks, then betweenness centrality has a very clear meaning of bridges, right? That, you know, these are the sort of the roads that go through the bridges. And so that sort of type of interpretation you can make on the centrality. I think I have another slide that shows you yet one more. Yeah, I have another slide that shows you, you know, one more picture of the centrality. It's again, you know, one network. This is actually called geometric network. And for this network, I calculated different centralities and color coded, you know, every node based on that centrality. Now, this is a geometric network, which means it's a network that sort of embedded on the plane surface, and you know, it has a lot strong local connectivities, and so that's why, for example, you don't see, you know, very large variation in the node degree, but still, you know, there are some nodes here with the high, you know, degree centrality. Now, closeness centrality again has its geometric meaning, and the nodes with the highest closeness centrality, they're like right here, you know, in the geometric center. Now, between the centrality, well, look at these nodes. They are sort of bridges connecting. You can probably see, you know, it's, I don't know which color to use. There's a lot of colors here, but these are the nodes that are connecting, that are bridges. You know, this is a bridge node, this is a bridge node, this is a bridge node. And eigenvector centrality is hard to, you know, detect, but you notice that there is a sort of group of nodes that are very well connected, you know, among them, and sort of a little bit separated from the rest of the network. And these are the guys who have high eigenvector centrality. By the way, this approach through the eigenvector centrality, we'll also look at it a little bit later when we start looking at the community detection. It happens that this approach also helps us detect communities. And, you know, looking at this picture, you kind of realize why, right? Because it sort of shows you those nodes that are very well connected, you know, among themselves. Okay, so sort of you start getting some sort of feeling, right, on the type of the centralities.
I have a question on eigenvector.
Sure.
On the picture, you want me to you have only one red community, but it seems that there are other communities. Why are not they red? So why don't they have also high eigenvector? I can't see why other groups of nodes that seem to be communities don't have this high eigenvector centrality and high those that are red.
I see. Well, you know, honestly, I don't know, like, if you look at this particular picture, why this group has been selected, right? It's, you know, probably there's some combination of the way things are connected that emphasize this particular group on this particular image. Overall, what you're going to get is, you're going to get, for every node, you're going to get the centrality metric, right? The centrality measure, and then you rank all the nodes by that measure. And so what happens is, those that are, you know, ranked high will typically be connected to those that are also ranked highly. You know, again, why in this particular graph we got like this group, but why, you know, this group is not considered to be very central. I mean, I guess if you look very closely, you realize that maybe these guys have a lot of, you know, many more connections among themselves than these guys have. But that's a sort of speculation. So, you know, I would say for the previous slide, for this one, it was a little bit more obvious that, you know, this group of nodes were the strongest sort of connection among them. But overall, I agree that, you know, the degree betweenness and closeness centrality, they are much more intuitive, you know, in terms of how you understand this. Eigenvector is a little bit harder. You have to get used to it, but that's sort of the one you use when you have somehow to describe this notion that, you know, powerful people connected to powerful people, right? Or important people connected to important people. So that's where that plays a role. Probably doesn't answer your question completely, but at least gives you sort of idea where to go.
Is it possible for a graph to have two communities with big
you know, I'll kind of postpone the question on community for like 2 lectures when we actually start talking about communities. But, you know, again, with the sort of with the eigenvector approach, you literally, for every node, you get a number. That the number will tell you this eigenvector centrality score for that node, and then you rank all the nodes by that score, And here we just sort of pick up like 6 nodes with the highest score. And on another graph, you just color coded them according to that score. So you know, in this picture, we didn't. What happened? In this picture, we did not do community detection per se. I just noticed that, look, you know, all the reds are connected to reds and all the greens are, you know, mostly connected to greens. And that means, you know, nodes with high eigenvector centrality tend to connect to nodes with high eigenvector centrality. Not always, right? There is a situation, right, like right here, when it is like, you know, there's red goes into green, but you know, otherwise it cannot be, because you know, you have the entire spread of centrality metrics. But as a tendency, you know, red will connect to red, like strong with strong and weak with weak. I'm sorry, I couldn't hear you this time. So eigenvector centrality has it's, you know, if you look at the formula, and you know, correct me if I'm wrong, asking you know, answering the question, because I might misheard you, but what's happening? But if you look at the formula itself, your, you know, the centrality is determined by the centrality of your neighbors, right? But of course, you know, the more neighbors you have, the higher the centrality will be, because you're adding up, you know, the centralities, or the you know, eigenvector centrality of those nodes. So yes, you know, the more connected node typically will have higher centrality, but you know, you're not just looking at the connections, you're looking at the importance of the nodes they are connected to. So there's just 2 factors, right? Number of connections and you know, the importance of your connections. So it could be, you can get a high centrality if, you know, your connections, you have a lot of connections, but they're sort of medium centrality, or you can get high centrality if you maybe have a few connections, but you're like really well connected to other nodes with high centrality. You know, you'll see this at play a little later when we talk about you know, community detection and clustering. Okay. Any other questions? Now, this is an important topic because, you know, it's very practical. So, you know, this is one of the things within this network theory that you will be using a lot in practice. So if you have more questions, Andrej will kind of help you to understand it better. So a couple more things, and then we actually have sort of second part where we need to talk about directed graphs. Here, what's important is the notion of centralization, which is what I'm trying to say is, you know, different networks have different structures, and some of them can be structured very, very centrally, and so they have this sort of like the situation with you know, the star, right, which is like very centralized structure, you know, it's a star. Or you can have a situation like a, you know, circle, which is, you know, the graph itself doesn't have any node better central than another, right? So, you know, in this case, in this kind of network, it's very clear that this node is much more central than others, and in this style of network, all nodes pretty much have the same you know, the same type of centrality, right? Equal values. So, and we want to differentiate at this moment. What we want to do is we want to compare the network to the network, and the metric that compares this is called centralization, and it just tells you how different are node centralities within the network. All right, so it actually just go through all the nodes, compute centralities for the nodes, and then compares them within the network, and just looks at the network that have like large difference in between centralities, or small difference between centralities. And that's what's called centralization. And you can also, of course, calculate centralization based on different type of centrality metric. And again, with iGraph, it's very easy to do. And the answer to the reason you want to do it is when you want to compare, again, two networks and see if one of them have more sort of central structure than another. For example, if you think about the network as a roads, say Moscow will have actually quite strong centralization the way it's built, right, with the rings and when the streets going away from the center. Other cities, you look at St. Petersburg or other cities, they have less centralization in this sense, right? In Moscow, it's red square, the center of the universe. Okay, so centralization is a property of a network, and it's based on comparing the values of centrality of every node in the network. Okay? All right, so let's move on. So now I actually want to switch gears a little bit and talk about directed graphs. And so when we have a directed graph, why do we need centralization? Again, centralization is when you want to compare two graphs between themselves, right? So it's not, centralization is a metric for the graph. So you want to see, like, again, like you want to compare two cities, their structure, without actually, looking at the map and spending a lot of time, like, finding the analogy between them. And I'm telling you that centralization, say, for Moscow and from New York City will be very different, because in New York, a lot of sort of, it's built on a grid, and so, a lot of sort of squares will have, a lot of points will have sort of equal centrality index, versus Moscow that is much more circular constructed. So it is to compare two different networks. It's a way to compare networks. Okay. All right. So directed graph. So what I was just talking about before, and from the very beginning up to this moment, was undirected network. So the network where there is no directions. Now, a lot of networks in real life, they do have directions, and that's, they form a directed graph. And when you have a directed graph, it becomes a little bit more complicated to, use the metrics we just described. And the reason for that is, okay, so, for a node, you might have, incoming links, right? And you might have like a lot of incoming links and say, two outgoing links. Well, is it a high degree centrality or low degree centrality, right? So that's why you distinguish usually out degree centrality and in degree centrality. So there is, in this case, out degree is 2 and in degree is, 6. But the things are getting more complicated when we start talking about, type of closeness centrality or betweenness centrality, because in both cases, what's important is the distances. And when you start having like one-way streets in the city, the distance, traveled by car or walked, on foot, where you can go against the one-way, they're very different. And so, you have to be very careful, how you define distances, because again, you might, again, if you're driving, like, say, in Moscow, there is only sort of one way to go around the Kremlin, right? So, what is it, clockwise? Yeah, it's clockwise. And if you need to go counterclockwise, it will take forever for you, right? So the distances in this sense, when you have one-way directions, is very hard to define well. It really depends on how you go. So the reason I'm talking about it is because the metrics of closeness centrality and betweenness centrality are based on distances, and distances are kind of poorly defined on the directed graphs, and so these metrics are rarely used for directed graphs. Well, they're used, but you have to be careful how you do it, because if you're not, you can get very, very strange results, right? So what I'm trying to say is, if you have a directed graph like this, right, the distance from node, this is node 1, 2, 3, right? The distance from node 3 to node 1 is equal to steps, and the distance from node 1 to node 3 is infinity, right? You cannot get there. Or let's say if this is a graph, the distance from 3 to 1 is 2, and the distance from 1 to 3 is 1, which sort of, a little strange, because you would think, okay, to get there, you should get there. So because of those strange things, again, closeness and betweenness is something that has to be used carefully. But degree centrality, as long as you take into account in degree and out degree, you're good. So what do you do with directed networks? Well, there is a, the story here goes back to, WebGraph and the algorithm that has been invented for, WebGraph. And I just want to remind you a little bit, how this WebGraph is built. So, we have web pages, and, when you have URLs on the web page, you click, you get onto another page. And that's a hyperlink. And so WebGraph is this graph of those hyperlinks where, each page connected to another page. And they're directed because, of course, you're clicking on the page, you get to another page. And the idea for the metric now, so the idea is that actually Google came up with, that we need somehow to rank those pages, right? And why do you need to rank the pages? Well, because when you do a search query, you need to get results, and those results, of course, based on the contextual match in between your search query and what's written on the page. But it would also be good to have some sort of input based on this on these links. And the reason for that is the following: when people point to your page from their pages, sort of giving URLs to a page, this is somewhat endorses you, right? They're telling you that, okay, well, this is a good page, I'm linking to this page. And it would be good to take this endorsement into account when you calculate, when you provide search results and rank them, gives us the sort of the ranking order of those results. And that's sort of that's the origin, of ranking on the graph. Now, just to without going too deep into the mathematics of this and into the details, in order to take those things into account, actually Sergey Brin and Larry Page, they're authors of this paper, the founders of Google, they propose the following model of the random walker. So imagine that you can actually, you're sitting, it's random surfer, random walker. So you're sitting on, you're browsing the web. They said, there are two things you can do. One thing is you can actually just sort of, you're on the page, you follow the link, you get onto another page. All right, then you read something, you see another link, you click on it, you follow, and you sort of keep following the links. Or, you can get bored, or maybe you get to the point where, there's no more outlinks, and then you just randomly open another page. So that's like that's the model circa 1998. Now today it would be probably more, sort of more appropriate to talk about you looking at, at the social network, and you're on somebody's profile. You look at their friends. Okay, you just click on the friend. You got on the friend's profile. You click on the friend. You got the friend's profile. Then you got tired of this. You either got onto like sort of random profile or you got back, right? So one of those sort of behaviors. But in any case, this behavior is very, very similar to the sort of random browsing or random walking on the graph. By random walking, I mean, you get to the page, and then the page can have multiple outgoing edges from it, and you just pick up one of those. And so that's exactly what those guys modeled. I understand now that they're probably, you guys, the linear algebra background is not strong enough for me to go into the details of the model, but the idea is the following. So random walker starts from some node and can follow out edges, and that's sort of you're clicking on URLs. But at some moment, it gets bored of doing it, and it can jump, to any other node in the graph. Okay, and so that's the model. And then the idea is the following: if this happens for a long, long time, then you can calculate the probability of being at the different nodes after a long, long time. And that probability is PageRank. And you can use it to rank the pages by their importance. So the probability that you end up on that page after a very long, long walk with a chance to sort of jump from one page to another, that's called PageRank. And this sort of jumps called teleportation. Now, sort of the good mental picture would be if you're in a city and you're just walking, and then any time to get to a corner, you take a random turn, take a random street, eventually, and then you just count how many times you come to different squares in the city. Eventually, you notice that you visit certain squares more often than others. Now, this is sort of model of walker. Now add to this model the sort of random jumps, which do not exist in the real world, but think about it like the following way. Okay, you hail a cab, you get a cab, and you just get in, and then you drop off somewhere. It will drop you off at some random location, right? So if you do that, eventually, again, you'll notice that you're more often appearing in certain parts of town or in certain squares. And then if you convert this into probability, then this is exactly the PageRank. So it's a probability that after a long walk with this sort of random jumps, you end up on certain pages or on certain squares in the city. I know this is very hand-wavy. Those of you who know linear algebra can look actually at those formulas and realize what I'm talking about. This is also called Markov chain or Markov process random walk on the graph. That's sort of more of a scientific term. I really don't want to go into a lot of details, on the math side of it. Is just because, again, you need some background to understand this. But I really wanted to talk about it because this is the way you can rank nodes when the graph is directed, when there is when you have direction of the edges. And here I show you a graph where every node, the size of the node is proportional to this PageRank. And in fact, it's extremely popular way of ranking on the graphs. It's so popular that there is like tons of other PageRank derived methods exist out there that are based on the PageRank that are used for other type of graphs where you have connections, right? And there is like TweetRank to rank Twitter messages. And there is SiteRank to rank citations, and there is BookRank to rank books, and bazillion of those ranks, and they all based on the idea that you can have items, and those items can be connected into a network, and the network will be directed, like one paper cites another paper, and that and that helps you to give them a rank, and ranking means calculate this metric, PageRank metric, for every node on the graph.
Isn't it close to Eigenvector?
Yes, it's a very good question. It is the same type of idea, except for it is done for directed graph. Now, just very simple eigenvector computations, it will be pretty much, okay, let me answer you precisely on this question. If you take this, random walk, remove the teleportation factor, so the sort of random jumps, and then do it on undirected graph, that will be your eigenvector centrality.
Okay, thank you.
Makes sense, right? Now, the difference here, that if you don't add this sort of teleportations, then this algorithm will not converge. The reason is because you might think about it as, you know, you will have nodes with incoming edges and no outgoing edges, and then your random walk will get stuck in this, for example, right? And so that's why you need this sort of chance to jump out of it. All right? Okay. And so, you know, this PageRank is extremely powerful thing. It's being used a lot, you know, everywhere. And if you have a directed graph, okay, guys, sorry. And so you have a directed graph, then this is the method of choice to rank the nodes on the graph. All right? Okay. So actually, you know, at this moment, I'm sorry. Okay, I need to take care of something else. I think we're done right now with this lecture. Ilya Andreevich, are you there?
Yes.
Excellent. So please take over. One thing we didn't cover was Hub's authorities, but I think, you know, you please, you know, go over those 2 slides on Hub's authorities, you know, later today. That might be helpful, but I want guys to actually first like get a little bit better understanding on PageRank.
Okay, so we start class in 10 minutes. Thank you.
All right. Thank you very much, guys.
Thank you.
Thank you. That's it for today. See you next week.